All right. So today we continue with trying to understand which conditions on a linear operator correspond to the property that this linear operator has a basis orthonormal basis consisting of eigenvectors, right? So remember, this is our picture or motivational picture. So we know that T, an operator T is diagonalizable, is equivalent to there is a basis consisting of eigenvectors for T, right? And similarly, we're trying to understand in the situation when we are, excuse me, in an inner product space. So we're trying to understand what corresponds to the property that there exists an orthonormal basis consisting of eigenvectors for T, right? Okay, so the question is what should be the corresponding property here, the property of the operator itself, right? So it should be something stronger than diagonalizable, but our task is to determine what should be the correct property. Okay, so first of all, let's try to note some pattern. So assume that this holds. Okay, so assume this holds for T. So the right-hand side, yeah. So T has a basis which is orthonormal and consists of eigenvectors. Okay, so T has a basis beta consisting, well, first of all, orthonormal. Let me write it maybe. Has an orthonormal basis beta consisting of eigenvalues for T, or eigenvectors, excuse me, eigenvectors. Okay, so assume such a basis exists. Then in particular, we can look at the matrix which represents T with respect to this basis beta, right? Okay, so since each vector in beta is an eigenvector, this means that this is a diagonal matrix, right? Because again, remember, like if each vector in beta is an eigenvector, then T of beta corresponds to T of V for any vector V in this basis corresponds to multiplying by some scalar. So from this, we know that it follows that the matrix is diagonal, right? And also, this time beta is an orthonormal basis, right? So let me stress it, an orthonormal basis. Then by a theorem we proved earlier, we know that the matrix representing the adjoint T star with respect to beta is going to be the adjoint of the matrix representing T with respect to beta, right? So we discussed this earlier. We know that with respect to an orthonormal basis, taking the adjoint corresponds to taking the adjoint of the matrix, right? Okay, but then this is also diagonal, right? Because what is the conjugate transpose or adjoint of a matrix? So it just means here we have to look at the matrix representing T beta, which is diagonal, right? So if you transpose it, it remains diagonal, and then you take the complex conjugate of each entry on the diagonal. So it stays diagonal, right? So we see that this matrix is diagonal as well, okay, for the adjoint, all right? And also we know that diagonal matrices commute. Okay. Meaning that the product of T star beta, the matrix, yeah, times the matrix representing T beta is equal to the product in the opposite order. So we can take first the matrix representing T and multiply it by the matrix representing the adjoint T star beta, right? Because if two matrices are diagonal, the order of the product of these two matrices doesn't matter. You get the same result. Remember, this is not true for general matrices, of course. Multiplication of matrices is not commutative in general, but for diagonal matrices it is, which is easy to see, right? And also remember that multiplying matrices corresponds to taking the composition, right? And so we can conclude that the linear operators T and T star also commute, right? Meaning that if I take the composition of T star T, it's the same as taking the composition of T star, right? Okay, so we see that this property, commuting with its adjoint, is a consequence of the property on the right-hand side. It is a consequence of admitting an orthonormal basis consisting of eigenvectors, okay? All right, so this property, as we will see, it's actually an important property. So we want to make a definition isolating this property formally. So let's assume that V is an inner product space, okay? And assume that T is the linear operator on V. Okay, then we say that this linear operator T is normal. Okay, it's normal. If we have that it commutes with the adjoint. So exactly the property we just observed. So T composition with T star is equal to T star composition with T. Okay, so this is for linear operators. And similarly, we can talk about normal matrices. So if A is an, let's say, n by n, so square matrix, real or complex matrix, okay, then we will say that A is normal. The matrix A is normal if we have the same, that it commutes with the adjoint. So we have A times A star. So now it's just the multiplication of matrices, right? Is the same as A star times A. Okay, so we have this this new property, normality, of matrices and linear operators. Okay, and using this terminology, what we have observed with respect to our question here, so we have observed that if the conclusion at this point is that if V has a basis, an orthonormal basis, of eigenvectors for T, then this implies that T is normal, right? This was the point of our early observation. And it's natural to ask if the converse holds as well, right? So now we ask if normality is the correct property that characterizes existence of orthonormal basis of eigenvectors. So we see we have implication in one direction. Let's try to understand if this is actually an equivalence, okay? So let's see. Okay, let me pause for a second here. All right, so let me move to a new page. So let's consider an example related to our question. So consider T, a linear operator on the vector space, or more precisely the inner product space R square with the standard inner product. So it's an operator which goes from R square to R square. Let this be the rotation by an angle theta, okay, for some fixed theta between 0 and pi. Okay, so let beta be the standard basis for R square. Okay, let me draw a little picture here. So how do we view the rotation operator? So this is R square, right? This is the x-axis, this is the y-axis. And assume I have a vector x, some vector in R square. So when we apply the linear operator t to it, what we get is the vector t of x, where the point of origin doesn't change, the length doesn't change, so the only change is that it rotates counterclockwise by an angle theta. So the angle between x and t of x is theta here. Okay, this is how this operator acts. So we can write out a matrix for it, for the rotation operator. Okay, so with respect to the standard basis, if we look at the matrix representing t with respect to beta, so the standard formula for rotation is the matrix consisting of cosine theta minus sine theta, sine theta, and cosine theta. Okay. So if you think about it, if you look at what happens to a vector, to the coordinates of the vector when you multiply by this, you will see it corresponds exactly to rotating by theta. All right. So this is the matrix. Now, what do we have? So if we calculate it, we have, I'm not going to spell out the calculation. You can do it yourself as an exercise. But what happens is that if we take A to be this matrix, okay, the matrix representing T, then we get that A times A conjugate is just the identity matrix, which is also the same as A star times A. Okay, so multiplying A with its conjugate transpose in either order gives us the identity operator. Okay, so in particular, we conclude that the linear operator T is normal according to our definition, right? Since it has this property. Okay, but very importantly, T has no eigenvectors at all. Okay, it has no eigenvectors at all. How do we know this? Well, let's think about it. So what it does, it rotates by an angle theta, right? But every vector, it means in particular that every vector gets rotated when you apply t. Like for every x, if it's non-zero and you apply t to it, it gets rotated. So it can't be just a scaled version of the previous vector, right? Like if you rotate, you cannot get this rotated vector as this vector times some scalar, because then all scalings of a given vector, they all lie on the line going through this vector, right? And if it's rotated by an angle theta, which is not zero, right? So it's a proper rotation, then there's no eigenvector at all. Okay. So as every non-zero vector gets rotated, which is not the same as getting scaled. Yeah, it can be represented by scaling. You can, this is a bit quick argument, right? Try to make it precise what I just said, but this is the point. All right, so this shows that the converse implication in our guess can actually fail for the field of real numbers. Okay, so this example shows that the converse implication, where I mean converse to this property, right? So we saw that orthonormal basis of eigenvectors for T implies T is normal, and we are wondering if the opposite implication holds. So this example shows that the opposite implication can fail for F, the field of real numbers. Okay, all right. However, luckily for us, at least for the complex numbers, we will be able to show the opposite implication. So it holds, but for complex numbers. Okay, so this is the next task. So we show that at least this converse implication holds for complex inner product spaces. So for the case when f is equal to c. All right. So it can fail over the reals, however, holds over the complex numbers. But we need to do a bit of work before we can show it. But that's our next aim. All right. Actually, let me pause here for a minute and switch to the next page. Okay, so this illustrates in particular difference between complex inner product spaces and real inner product spaces. Yeah, so some things can be true for in one case, but not in the other. It's important to know, to remember. All right. So now let's obtain some results which lead us to showing this implication for complex inner product spaces. So we begin with theorem 615, which tells us a number of properties of inner product spaces and normal operators. So the situation is as follows. Assume V is an inner product space, okay? And assume that T is a linear operator on V, which is moreover normal. So commutes with its adjoint, okay? Then we have the following properties of T. A, look at T of X and look at the norm of this vector. Then it's going to be equal to the norm of T star of X, okay? For all vectors X in V, okay? So this tells us that the length of the vectors are the same, independent of whether you apply T or the adjoint of T in the normal case. B, we have that T minus C times I, where I is the identity operator on V. So this is normal, itself a normal operator for all scalars C in F. Okay. The next property, if X is an eigenvector of T, then X is also an eigenvector of T star. All right. And in fact, we have that if T of X corresponds to multiplying by lambda, so equal to lambda X, then T star of X is equal to the complex conjugate of lambda times X. Okay. Note here that again, our assumption is that T is a normal operator. So this wouldn't be true in general for a general linear operator, but for normal it is true. And D, if we have two distinct scalars, lambda 1 not equal to lambda 2, and assume they are both eigenvectors, eigenvalues, excuse me, eigenvalues of T with corresponding eigenvectors x1 and x2, okay? Then, so distinct, we have two distinct eigenvalues. Then the vectors corresponding to them are orthogonal. So then x1 and x2 are orthogonal. Okay. So in a usual vector space, we know that eigenvectors corresponding to distinct eigenvalues are linearly independent. But here we see that for normal operators, we have something even stronger, that they in fact are orthogonal. All right. So this is the theorem, which collects a bunch of properties of normal operators. So now let's prove these assertions. Okay. So let's start with the first one. So we need to show that given a vector x, so okay, so fix x. So for any x in V, we have the following sequence of equivalences. And so the idea here is that the norm can be expressed in terms of the inner product, right? So remember the linear operator T and its adjoint, how are they connected? Why this formula in terms of the inner products, right? So then whenever we want to show something like this, we want to connect them using that formula. Okay, so we can do it here as follows. So let's look at the norm of t of x. Okay, we know that the square of the norm, by definition, is the inner product of t of x with itself, right? Because remember, the norm is defined as the square root of the inner product of a vector with itself, right? So this is just by definition of norm, all right? But now this can be written as t of x inner product with t star of x. Okay, so this is theorem 611D. So this is a theorem which tells us that for a linear operator, its double adjoint is the same as t itself, right? So the adjoint of an adjoint is just t itself. So we have this, but then this is equal to taking t star t of x inner product with x. Okay, and this is just the definition of a joint operator. So here I wrote it as composition, right? So what it should be saying is we take t star of t of x, right? This is how we apply the formula. Okay, so we have this, but now this in turn is equal to t composition t star of x, x. And this is the point where we use that the operator is normal, right? So as t is normal. So we use that t star t is equal to t star, composition in the opposite order. Okay, but now this can be written as t star of x, t star of x. And this is again by the definition of a joint operator. Right? Because you can think about this as t of t star of x inner product with x, right? But then this is the same as the argument here, t star of x inner product with t star of x, because here we are applying t, right? So this is just the definition of the joint operator. Okay, but look, what we got here is this is the same as the norm of t star of x squared, right? Inner product of t star of x with itself. So the conclusion is that the squares of the norms are the same, right? But then we have that the norms are also the same. So t of x, the norm of t of x is equal to the norm of t star of x, because norm of a vector is always non-negative. So remember, this is one of the properties of norms. Non-negative. So if the squares are equal, then the norms themselves are equal. Okay, so this gives the first property, A. Okay, now let's prove the second. So let's show that, so B, okay, B. So now we want to show that this operator T minus C times the identity is normal, no matter what scalar we take. So here we use properties of adjoint and how they interact with operations, right? So this was theorem 611. So by the theorem we have that if we look at T minus Ci adjoint, okay, this is going to be the same as T adjoint minus the complex conjugate of C I adjoint, but the adjoint of the identity operator is again the identity operator, right? So this is simply T star minus C bar I, okay? So this is the adjoint of this operator, okay? So now let's look at the product of this operator t minus ci with the adjoint. So t minus ci star, right? Because remember, we are trying to show that this is a normal operator. So we have to show that it commutes, right, with its adjoint. So we look at this product, okay, and try to show that it's equal to the product in the opposite direction. So, okay, so we're given this. Now use the previous line here. So we get that this is t minus ci. And here times is composition, right? Because we are talking about linear operators. So this is t star minus c bar I. Okay. So now let's open the brackets. So we use the properties of composition and sum of linear operators and multiplication by scalars, right? Which are basically like the rules of algebra. So we get that this is equal to the composition t star minus t composition c bar I minus c times I composition with t star plus c I composition with c bar I. Okay. So, and again, remember, these are all linear operators here. Okay. Okay, let's simplify this. So, so we get the first one. Look, the first one, t star. So we assuming that t is normal, right? So it means we can change the order here. So we can write t star t. Okay. So st is normal. All right. Then we can here we have minus c bar I t, and this is using that t is linear. Okay, so st is linear because look, when we have this composition here, it means we are first applying c bar I and then we applying t. But because t is linear, multiplying by the argument by a scalar corresponds to multiply to the scalar times t of the argument, right? So so we get this by linearity of t. Similarly for the next summand, so we have minus t star ci, and here we are using that t star is linear in this expression, right? Okay, and what remains is we have plus what c bar I times ci. So here note I'm changing the order, and again this is because I is just the identity operator, right? So then this whole expression simply corresponds to first multiplying by c bar and then multiplying by c. That's what this operator does. But this is the same as the first multiplying by c and then multiplying by c bar, right? Because multiplication in the field is commutative. Okay, so we have basically swapped the expression in every summand, right? Okay, so we have this. All right, so now let's look at the product in the opposite direction. So we will return here in a second. Let me now multiply in the opposite order. So here we multiply in the order the operator times the conjugate. Now let's do conjugate times the linear operator. So for this, we look at the product t minus ci conjugate times t minus ci. And the hope is to get exactly the same expression as we had earlier, right? Okay, but look, this is going to be, again, t star minus c bar I, right? That's the expression for the conjugate, times t minus ci. All right, now just open the brackets. So this is t star t minus t star ci minus t star, excuse me, too many t stars. Okay, so this is the first times second, first times this. Now we have this times this. So this should be c bar it and plus c bar I ci. Okay. So look, we have this expression Unfortunately, it's on different pages, which is not ideal. Okay, but look, we have this expression. And if I go back, we look what expression we have here. This is the same. Okay, so double check, but this is the same expression. And so what we get is that t minus ci times t minus ci star is equal to t minus ci star times t minus ci. Okay. So the conclusion is that the linear operator t minus ci is normal, as promised. Okay, so this proves B. Okay, let me pause for a second. Okay, so let's prove the next item, C, about eigenvectors, yeah? That T and T star for a normal operator have the same eigenvectors. Okay, so suppose that T of x is equal to lambda x for some vector x in V and some scalar lambda in F. Okay, so I'm given this. Our task is to show that then x is an eigenvector for T star as well. Okay, so let us write U to denote this expression T minus lambda I. So this is a linear operator again, right? Okay, so then because we have that this is an eigenvector, so we have this equality. So what we get is that U of x is equal to 0, right? So we have U of x is equal to 0. And we also know that U is normal by B, right? Because we just proved that if T is normal, then the operator defined like U, where in this case the scalar C corresponds to the scalar lambda here. So this is normal, okay? But then by A applied to the normal operator U, we have that 0, which is the norm of U of x, right? Because U of x is 0, so the norm of the 0 vector is 0. Then the norm of this is equal to the norm of the adjoint of x, so U star of x. Okay, so now this we can express as so because we know that U is given by this expression, right? So then the adjoint of U can be written as T star minus lambda complex conjugate I of x. Okay. But now this in turn is simply the norm of T star of x minus lambda bar times x. Right, just applying this operator in brackets. Okay, but this norm is equal to 0 again, right? Because we started with saying that this is equal to 0. So we get that the norm of this difference is 0. But this means that, again, because the only vector of norm 0 is 0. So hence we have that T star of x is equal to lambda bar times x. And this is exactly what we wanted to show. So this shows that x is an eigenvector for T star with the corresponding eigenvalue lambda bar, where lambda was the eigenvalue corresponding to x for T. Okay, so this shows part C. And finally, let's show D. So let's show that if we have two distinct eigenvalues, then the corresponding eigenvectors are orthogonal. Okay, so D, assume lambda 1 different from lambda 2 are two eigenvalues of T with corresponding eigenvectors x1, x2. Okay. So now applying C, we have the following. Let's look at lambda 1 times the inner product of x1, x2. Okay. By linearity of the inner product, because it's bilinear, we have that this is the same as the inner product of lambda 1 x1 inner product with x2, right? Now, lambda 1 times x1 is simply t of x1, because we're assuming, right, that x1 is an eigenvector corresponding to lambda 1. So we get this. Now, using the property of the adjoint operator, we have that this is the same as x1 inner product with t star of x2. Okay, but now this is equal to x1 inner product with lambda 2 bar x2, right? This is where I'm using C, because we started with assuming that x2 was an eigenvector for t corresponding to lambda 2, right? So according to C, it then means that x2 is an eigenvector for t star with an eigenvalue lambda 2 bar, the complex conjugate. You see? So we just plug it in. So this is the part that uses C. Okay. But if we have this, now what is this? So we can take lambda 2 out, and we have to take the complex conjugate again, right? So we get lambda 2 complex conjugate, inner product x1, x2, which is simply lambda 2 inner product x1, x2. Okay. And remember, by assumption, lambda 1 is not equal to lambda 2, but we have this equality here, that lambda 1 times x1 inner product x2 is equal to lambda 2 inner product x1, x2. So this equality can only happen then when the inner product itself is 0. So this implies that the inner product x1, x2 is equal to 0, right? And this precisely means that they are orthogonal, right? So x1, x2 are orthogonal vectors. Okay, so this concludes the proof of the theorem, of the last part of the theorem D. All right. Okay, so now with this result at hand, well, let me pause again for a second. But with this result at hand, we can finally fulfill the promise and prove, remember that converse implication for complex inner product spaces. That normality corresponds to the existence of an orthonormal basis consisting of eigenvectors. So I'm going to switch to a new page if there are no questions. And this is going to be theorem 616. So let T be a linear operator on V, and assume that V is a complex inner product space. So KIPS, okay? Complex inner product space of finite dimension. So the dimension of V is smaller than infinity, okay? In this case, we can show that T is normal if and only if there exists an orthonormal basis for V consisting of eigenvectors for T. Okay, so we get the equivalent, the desired equivalence here in the case of complex inner product spaces. So we already know one implication, right? So proof. So this implication from right to left, we already know. We proved it just before the definition of normal, the definition of normality, right? So we know that basis of orthonormal basis of eigenvectors implies normality. So the task is then to show the converse implication, the difficult direction. Okay. So towards this purpose, we suppose that T is normal. Okay. Now, how do we use that this is a complex inner product space? So we use it because the point is that over complex numbers, every polynomial splits by the fundamental theorem of algebra. Okay. So by the fundamental theorem of algebra, every polynomial over the field of complex numbers splits. Okay, so that's the only reason why we need that this is a complex inner product space as opposed to real inner product space. So what we get is that every polynomial splits. So in particular, the characteristic polynomial of T also splits. Right? Because every polynomial splits. Okay. So we have a result about such situations, right? We know that by Schur's theorem, this was theorem 614. If the characteristic polynomial of a linear operator splits, then there exists an orthonormal basis that's denoted beta, consisting of V1 through Vn, where n is the dimension of V. So there is a basis like this for V, such that the matrix representing T with respect to this basis beta is upper triangular. Okay, so this was the point of Schur's theorem. Then, in particular, okay, maybe let me just draw it quickly. So we have that the matrix representing it is upper triangular like this. So we have zeros below. So in particular, look at the first entry in the position 1, 1. So the column corresponding to this entry has zeros everywhere else, right? And just some entry on the diagonal. So this means that the vector V1 of the basis beta is an eigenvector of T, right? Because, again, let me repeat what I just said. So since the matrix is upper triangular, we have that the column vector representing the coordinates, so T V1 with respect to beta, has the form lambda 0, 0 for some lambda, the scalar in F. Okay, so we have that T of V1 is equal to lambda V1. Okay, so this demonstrates that it is indeed an eigenvector. Okay, so now we want to argue inductively. So assume that V1 through Vk minus 1 are eigenvectors of T. We claim that then Vk is also an eigenvector of T. Okay, because then by induction, starting with V1, because we just observed that V1 is an eigenvector. So if we can prove this claim, then by induction, we can show that V1 is an eigenvector, then V2 is an eigenvector, etc. So we would show that all vectors in beta I eigenvectors of T and hence we would be done, right? So the whole point reduces to showing this claim now. All right, so let's show it. So consider any index j smaller than k, and let lambda j be the scalar in F. Let it denote the eigenvalue of t corresponding to Vj. Okay, by assumption, it's Vj is an eigenvector, so we have some eigenvalue. Now, by theorem 615 that we just proved, we know that T star of Vj is equal to lambda j bar complex conjugate times Vj. Okay, so we know this. And we have the following calculation. So I'm going to switch to the next page. So I look at the vector T of Vk. So this is the vector for which we want to prove that it is an eigenvector. And look at its coordinate vector with respect to beta. Now this corresponds to A times Vk with respect to beta, right? Remember, A is the matrix representing T. So applying T corresponds to multiplying by A, right? So multiply by A. Now this is the same as A times, and now what do we know about this vector? So we know that we have zeros, then we have 1, and then we have zeros again, right? Where this is the first k minus 1 columns. This is we have 1 in the kth position, and we have zeros after that again, n minus k. Okay, so let's spell this out. So this corresponds to a11 times 0 plus etc. plus a1 k minus 1 times 0, right? Plus a1 k times 1 plus a1 k plus 1 times 0 plus etc. plus a1 n times 0. Okay, so this is the first column. So we only have one non-zero entry here. Similarly for each row of the vector. And for the last one, we have a n1 times 0 plus etc. plus a n k minus 1 times 0 plus a n k times 1, again the only non-zero entry, plus a n k plus 1 times 0 plus etc. plus a n n times 0. Okay, so all I'm doing here is just writing out what it means to multiply this vector by a matrix. So we see that almost everything is 0 in the sums. So what remains things in this column. So we're left with a1k, etc., a-n-k, right? This is the vector. But this is the same as a1k through a-k-k. And after that, we have zeros, right? So we know this because aik is equal to 0 for all I greater than k, since the matrix A is upper triangular. Okay, so it's a bit tedious calculation, but the point is that we can write out the coordinate vector for this. Okay, so in other words, we have that T of Vk is equal to a1k times v1 plus etc. plus akk times vk, right? Okay, so we got this expression. And finally, by corollary to theorem 6.5, we have that AJK is given by the inner product T of VK Vj, right? This is equal to Vk T star of Vj by the property of the adjoints. And the previous one was simply because the coordinates, we know that with respect to an orthogonal basis, the coordinates are expressed in this explicit form, right? So this is the same as Vk lambda j bar Vj. This is the same as, now we just take lambda j out and conjugate times the inner product Vk Vj. But this is equal to 0 because, again, beta is an orthogonal basis in particular. So beta is orthogonal. Okay, so what we have obtained is that AJK is 0. And since this holds for every j less than k, because remember, j was an arbitrary index smaller than k, we are done, right? Because then we can conclude that T of Vk is equal to AKK times Vk. Because all the previous coordinates here are all 0, except for this last one. Okay, so we get this, right? But this means that this is an eigenvector. So hence, Vk is an eigenvector of T. Okay, so this concludes the inductive step. And so we have demonstrated that all vectors in the basis beta, which is an orthonormal basis, so all vectors in it are eigenvectors. And that's exactly what we wanted to show, right? So normality implies that all vectors in the base, in some bases, in some orthonormal bases, consisting of eigenvectors. Okay. Yeah, sorry if it was a bit fast, but you can just redo this calculation. It's not difficult. You just a bit tedious because you kind of have to spell out this whole product carefully. Yeah. All right. So this concludes the proof of the theorem in the complex inner product spaces case, right? So next time we'll discuss what happens for real inner product spaces. Can I go back? Sure. Yes. Yes. Okay. So yeah. So this describes the situation for complex inner product spaces, and for real, the situation is a bit more subtle. So we'll try to understand it next time, what is missing. Once again, we only use the complex, the fact that the field of scalars is the complex numbers here to deduce that the characteristic polynomial splits, right? Just because over complex numbers, every polynomial splits. That was the sole use of the complex inner product space here. In the real inner product space, it may not be true. So we'll have to understand what happens instead next time. All right, thank you very much. I'll stop here.